Hello, everyone. Thank you for subscribing to this webinar on data analysis in the medical research field, part 1, introduction and basic tests. So this is part 1, which means there is at least a part 2. Tomorrow, part 2 of this series will take place, and we will be talking a little bit more about multivariate analysis in medical research, as well as survival analysis. This webinar will be illustrated by the ExcelStat statistical software that works as an add-on to Excel. My name is Jean-Paul Malouf. I am a data science consultant at ExcelStat. I will try to be as intuitive as I can in my speech and avoid reference to mathematical formula. But anyway, you should know that the statistical tools that we use in epidemiology or in medical research in general, there are so many of them. Today, we'll only see an overview of the mainstream methods that we use in this field, and we won't be able to get into the deep details of these mainstream methods. You should know that there's a download section in this webinar platform, so you can download the handouts, so in PDF, as well as the data I will be using to illustrate the webinar. At the end of the webinar, there will be a Q&A session, so don't hesitate to submit your questions in the chatting box. I will try to answer as many as I can at the end. Here's a small outline of what we're going to see today. I'll start with a few words on ExcelStat, then an introduction and some terminology. So there are some words I will be using quite often, such as variable or qualitative variable or quantitative variable. We will see in this webinar that we'll be mainly focusing on the study of how a set of variables, which we call risk factors, for instance, or independent variables, will influence a clinical outcome, which we'll call dependent variables. And these variables can be either quantitative or qualitative. We will see many possible situations today. We'll see how to investigate the effect of a qualitative variable on a quantitative clinical outcome, how to investigate the effect of a qualitative variable on a qualitative outcome, and at last, quantitative versus quantitative. Okay, but first, let me tell you a little bit about ExcelStat. ExcelStat is a statistical software that works as an add-on to Excel on PC and on Mac. It's also available for Excel 365 and Google Sheets, so you can also use it on the cloud. ExcelStat in a few numbers holds more than 220 statistical features. It has more than 150K users worldwide, more than 25 employees at your service, 300K monthly visits on the website, and the software is available in 7 languages and has offices in 3 different time zones, so America, Europe, and Japan. The software is downloaded 10K times every month. The software is developed by the Adinsoft company, which is hosted in the Data Factory. The Data Factory is a private laboratory dedicated to data science, which is located in Bordeaux in France. It holds more than 5 expert companies, including Adinsoft, and it organizes more than 25 workshops, events, and training every year around data science. ExcelStat is organized in 8 different solutions to meet your specific needs. So there are generalist solutions, which are Basic, Basic Plus, and Premium. Basic includes tools, statistical tools to explore, visualize, and model your data in one single interface. Then Basic Plus has all of the basic features plus essential machine learning tools for prediction. Premium includes the complete 220 ExcelStat features. Between Basic Plus and Premium, you have intermediate solutions. You can find intermediate solutions such as sensory, life sciences, marketing, forecasting, and quality. And these solutions are field-oriented. For instance, sensory for sensometricians. And maybe for you, the most appropriate solution would be life sciences for the analysis of medical and biological data. Anyway, what we will see today, the tools we're going to see today, are included in all ExcelStat solutions, even the basic solution. But what we're going to see tomorrow in the second part of the webinar is partly part of all the solutions. Otherwise, there are a few tools which are only part of life sciences and premium. So this is for tomorrow's webinar. But for today, all the tools we are going to see are part of all solutions. There are more than 220 tutorials associated to downloadable datasets available at the ExcelStat website. So you should know that every feature in ExcelStat has its own dedicated tutorial online. If you're ever lost in using this or that feature, you have a step-by-step tutorial that guides you through the configuration of the dialog box and the interpretation of the results with an intuitive explanation of how the feature works. We also develop a YouTube channel, which is called Stat Cafe, which shows you short videos, each video dedicated to a specific statistical feature, so with short explanations and applications using ExcelStat. You can access the channel by clicking on your PDF right here. ExcelStat also holds a page with free webinar recordings. So a few months ago, we ran webinars on general statistics, so not field-oriented. So there are 5 webinars on general statistics, such as describing data, exploring and clustering data, statistical testing, modeling variance, and there's a 6th one also, machine learning and prediction. So if you're ever interested in basic statistics, I would recommend checking these webinars. You can also access this page by clicking on the PDF. And also you should know that the webinars on medical research will be accessible as well on this page. So within 2 weeks, you will access the recording of the current webinar by clicking on this link here. The upcoming webinar, so tomorrow's webinar, is accessible for registration through this button. So if you're ever interested, don't hesitate to register by clicking here, okay? Now let us get into the details of this webinar, introduction and some terminology. What is a study design first? A study design is a set of methods and procedures used to collect and analyze data in the framework of a particular research problem. And in medical research, study designs include very famous designs, maybe you already heard of them, cross-sectional studies, cohort studies, case control studies, clinical trials, and more. So I have included in this PDF an appendix which describes quickly each of these study designs, if you're ever interested in getting more into the details of these designs. Now, there's a word I'll be repeating quite often during this webinar. It's variable. What is a variable? A variable is a measurable element which can take different values. So variables include roughly 2 kinds of variables: qualitative, which we also call categorical, and which we cannot express in terms of numbers, which we cannot quantify. So these variables include the gender, for instance, presence or absence of a disease in a patient, the treatment administered to a patient, drug A, drug B, or placebo. Variables also include quantitative or numeric variables, such as renal clearance, weight, systolic blood pressure. So these variables, you can express them in quantitative scales, numeric scales. Now, I'm going to show you another categorization of variables in medical research or in statistical modeling in general. In medical research, we usually investigate the relationship between 2 classes of variables. So independent on one side and dependent on the other side. So dependent variables are clinical outcomes, such as the occurrence of an event, such as death or relapse or recovery. And the independent variables include like risk factors. For instance, I don't know, the age, or it could be the gender, or it could be the drug which was administered, or it could be the cholesterol concentration in the blood. So independent variables are the variables whose effect on the outcome is being studied, and they include age, gender, cholesterol, smoking habits, drug administration, drug or placebo. And notice that independent variables include both qualitative and quantitative variables. So age, cholesterol, weight are quantitative, Whereas gender, drug administration, smoking habits are more qualitative. Okay. Dependent or outcome variables are the variables that change as a consequence of independent variables. For instance, disease, yes, no, survival, yes, no, the systolic blood pressure, time to disease. So here also we have several kinds of variables, like qualitative, such as disease or survival, quantitative, such as systolic blood pressure, and this is a very special case of variables, the time to disease, time to an event, which we'll be investigating more tomorrow using survival analysis. Okay, so independent variables influence dependent variables, and the main thing about medical research and epidemiology, and in the webinars today and tomorrow, will be to see how to establish a link between independent variables and dependent variables, how to know whether age influences systolic blood pressure or whether cholesterol influences a disease. Okay, we will see several cases where independent variables are quantitative or qualitative, and cases where dependent variables are quantitative or qualitative. So just for you to know, study designs in clinical research can be categorized like this in this very famous pyramid. I don't know if you've already seen this kind of figures. The study designs are sorted in order of strength of evidence. So the higher you are in the pyramid, the more the study design is able to establish a causal relationship between independent variables and outcomes. Okay. So randomized controlled trials in which you really have a control over the independent variable because you are experimentally manipulating it. Randomized controlled trials are among the best study designs to establish a causal relationship between the independent variable and the outcome. Okay, so this one is experimental. These are more observational. So in cohort studies, in case control studies, and all the other studies, we investigate more independent variables which are inherent to the patient, such as the age, the gender, or the exposure to some risk factors. So these studies are more observational. We are not manipulating any drug administration or any placebo administration. Then there's another way to categorize clinical research study designs. The descriptive studies and the analytic studies. Descriptive studies are used to generate hypotheses and plan for analytic studies. So you cannot really establish causal relationships between independent variables and outcomes using these kinds of studies. And you can just explore things and generate hypotheses that you will be able to test using analytic study designs, such as cohort analysis or case control studies or randomized controlled trials. There are many more, which I haven't included in this pyramid. Don't hesitate to do some more research if you're not familiar with this to learn more about study designs. Now, how does medical data set look like? Very often you will have something that looks like this. So this is a case control study where incident cases of leprosy in a region of northern Malawi were compared with population controls. This means that we have a group of patients suffering from leprosy, which we compared to a similar group of healthy people. In rows here, we have patients. We have one patient per row. And here we have an outcome variable, which is case or control. So 0 means the patient is part of the healthy group, and 1 means the patient is part of the case group. 1 means the patient has the disease. In between, you have independent variables, so the age, sex, the vaccine scar, school, type of house, and we'll be interested in evaluating the influence of each of these independent variables on the outcome. So this will be our leitmotif for today and tomorrow. So now that we have data in hand, what should we do? This is a suggestion. If you're not familiar with statistical analysis, this is a small suggestion from me to you. First, describe, of course, and clean the data. Then assess the effects of the independent variables on the outcome using statistical testing and modeling. Now, how to choose the appropriate descriptive tool or the appropriate testing or modeling tool. Here are a few guides. These are some statistical methods for data description. According to the type of variables you want to describe, there are mainstream statistical methods that I recommend. So for instance, if you have qualitative variables, you want to study, I don't know, the gender or I don't know, or this type of house variable, you can use these statistical methods. If you have quantitative variables, numeric, such as blood pressure, cholesterol, and stuff like that, you can use central tendency, dispersion, and histogram statistics. If you want to investigate the link between two qualitative variables, for instance, the link between intervention and recovery, you can use a crosstab. Link between two quantitative, you can use scatterplot, correlation coefficients, and so on. Okay. Then this was for describing data. What about this part? I've also included a guide that will help you. You have links also here for more resources to know which tool to use at what time. So this one is for assessing the effect of the independent variable on the outcome, how to assess statistically the effect of one variable on the outcome. So according to the type of independent variables and the type of dependent variables, I've included examples for you, as well as mainstream statistical methods. So this guide is a kind of wrapper of 3 statistical guides, which are much more expanded than this, and which are available for free on the ExcelStat website, so you can check them out. There's one for statistical testing, one for modeling, and one for survival analysis. Okay. Now, what will we be seeing today? We'll be seeing these 3 cases. We'll be investigating the effect of one qualitative variable on one quantitative, one qualitative on one qualitative, and one quantitative on one quantitative. Tomorrow, we'll see the rest. Let's begin. Randomized clinical trial example. I'm going to investigate the effect of a qualitative variable on a quantitative outcome. So this is the first case in the table I just showed you. We want to study the influence of a new drug on systolic blood pressure in patients suffering from coronary artery disease. 40 patients receive a placebo and 40 others receive the drug under the same conditions. So their systolic pressure is measured 2 hours later. So we are experimentally controlling the effect of the independent variable here. So this is one of the strongest designs we can use to establish a causal relationship between independent and dependent variable, because we are really manipulating experimentally the independent variable. Is there a difference in mean systolic pressure between patients who receive the placebo and those who receive the drug? So this is our main question. This is how the data looks like. Once again, you have 1 patient per row. The data are made up. Then we have the independent variable, which is drug administration. So some patients receive a placebo, other patients receive drug treatment, and after 2 hours, we measure the dependent variable, the clinical outcome, which is systolic blood pressure, and which is quantitative. So this is qualitative, this is quantitative. So let's start by describing the data, and we will see how important it is to do so. So this is the data which is within Excel, and this is ExcelStat, which is an additional tab that works as an add-on to Excel. So in ExcelStat, you have several menus, which give you access to several statistical features. So features for data analysis, for data modeling, so on. And here we have advanced features that are part of more intermediate solutions between basic and premium. Tomorrow we'll be using the survival analysis menu, but today we'll just be focusing on these menus here. So I will go to descriptive data and descriptive statistics. So this is a typical ExcelStat dialog box that includes several tabs. So general tab, options tab, outputs tab, charts tab. Within each tab, you can select data within different fields and configure the different options you're interested in. So don't look at the D column now. For now, we're just concentrating on the first 3 columns. So we want to describe systolic pressure. So I will just select systolic pressure in this field here. I can select it either like this by clicking on the C here, or I can select it like this. I would strongly recommend that your data set starts at the first row in Excel before running any statistical analysis. And I would recommend also avoiding elements or things under the table here. So I will select the data like this. Then I want to obtain statistics of systolic pressure according to treatment. So I will select treatment as some samples here. In the outputs tab, I can select all the statistics I want to investigate. So I want to compute minimum, maximum, quartiles, median, mean, variance, standard deviation, and so on. In the charts tab, I want to ask for several quantitative data options: box plots, scatter plots, strip plots. And the options sub-tab, I will recommend grouping the plots. Here I'd like to have the labels below, and we'll see what will happen. So I click OK. There are the results that appear in a new Excel spreadsheet. Of course, you can manipulate them as you're used to manipulate Excel files and spreadsheets. So we have the mean, we have the variance, the standard deviation, the minimum and the maximum. Do you see something weird happening here? Do you notice that in the placebo group, we have systolic blood pressures of 0? Is this normal? I don't think so. And in the systolic blood pressure for the drug group, we have a value of 1090. This is also not normal. So there's something weird happening in the data. And the fact that we ran descriptive statistics before running any test or any statistical model allowed us to avoid making wrong decisions by running directly to the test and not taking the time to describe the data. So this is a very important step to have prior to any analysis in statistics. So let's see what happened in the data. I'm going to apply an Excel filter, okay, and try to check these data points. So I will select the 0 and the big one here. So we have 3 data points that are concerned by mistake. So after reviewing what happened in the research process, we realized that the person who entered the data entered missing data points as 0. So the problem is when you enter missing data points as 0 will be that the software will consider it as a data value. So when you will compute the mean systolic pressure for placebo, it will be influenced by these 0 values. So as they are missing values, I just leave blank cells here. Then this one, we realized that it was simply a typo, and we'll just correct it and have the right answer like this. So I will select my data once again and run the analysis all over again. Now to run the descriptive statistics analysis all over again, I can go back to my report and click on replay here. And I have the dialog box, which is already pre-configured in a way to obtain the equivalent report. So I click OK. And now everything seems much better. So minimums and maximums are all right. Now let us check the mean. We see that for the placebo, the systolic blood pressure is much higher on average than for the drug. So this is one first tendency or one first trend we are already seeing using simply descriptive statistics. Then right under you have some charts I will be commenting on. So within each chart, you have the same y-axis, systolic pressure, and x-axis, so the treatment, drug or placebo. In this case, we have box plots, here we have strip plots, and here we have scattergrams. In all cases, we have the same conclusion. We notice that the placebo data are higher in terms of systolic pressure than the drug data. So in all cases, the plus corresponds to the mean. The middle dash, here in red and here in black, corresponds to the median. And here each green dash corresponds to one data point. So descriptive statistics allowed us to do two things. First, notice that there were some mistakes in the data that had to be cleaned. And second, to notice the first trends in the data and to try to see what to expect out of the statistical test that will help us investigate the relationship between systolic pressure and treatment. So it's a very, very important step. Describing data is very, very important. Now let us move on to the second step, assessing the effect of the independent variable on the outcome. So I get back to this guide, which you will be able to use on your side. In our case, we have one qualitative variable as an independent variable. So our independent variable is drug versus placebo. This is qualitative. And the dependent variable is quantitative, so blood pressure. So in this situation, we're going to use the two-sample t-test because we have two groups, drug and placebo. If you had more than two groups, you could have used ANOVA. So here's a small reminder on how to interpret the outcome of a statistical test. A statistical test usually helps answering a question whose answer is yes or no. For instance, is mean A significantly different from mean B? Is mean systolic blood pressure from the drug group significantly different from the mean systolic blood pressure from the second group? Statistical tests involve two hypotheses which are opposite to one another. The null hypothesis, which generally implies an idea of equality, so mean A equals mean B, and an alternative hypothesis, which generally implies an idea of a difference, mean A is different from mean B. The test will compute a number, which is called the p-value. The p-value, which is confined between 0 and 1. This is a probability value. And how can we take a decision out of the p-value? We compare it to a risk threshold that we call alpha. And this is a risk threshold you should be defining prior to the study and according to the severity you want to have in making a decision or not, according to the strength of the effect. But very often, researchers set alpha at 0.05, but this is not necessarily a reason to have it systematically at 0.05. So if you want to learn more about alpha and p-values, don't hesitate to check the webinar on statistical testing here. Anyway, as soon as you get your p-value out of the statistical test, you compare it to your risk threshold alpha. If it's smaller than alpha, you can reject the null hypothesis and accept the alternative hypothesis while taking a risk proportional to the p-value of being wrong. Okay, so more generally, we say that if the p-value is low enough, if it's lower than alpha, we say we have a significant effect. There is a significant effect of drug administration on mean systolic blood pressure, for instance. Now we're going to run the student's t-test for two independent samples, as I told you. Classic tests, such as student's two-sample t-test, are only valid under certain conditions. And for student's t-test for two independent samples, you should have independent measurements, so only one measurement per patient. Group variances should be equal. You should have the same dispersion, the same variance between the two groups. You can test for the equality of variances by using a statistical test. So there are statistical tests for this in ExcelStat. And you need to have at least 30 patients, 30 individuals per group, or if this is not the case, the normality for each group assumed or verified. So for more information about normality, you can check the descriptive statistics webinar that we've seen a few months ago. Now, the conditions of validity for parametric tests can all be found here on this link. Now, say we checked for the validity conditions and we want to run the test. I will go to test the hypothesis, parametric tests, and use the two-sample t-test and z-test. First of all, I need to check the data format I have. I have one column per variable. Each column corresponds to one variable. So this is good. In the data field, I will select my dependent variable, this one, systolic pressure. And in sample identifiers, I will select my treatment. Okay. In the options tab, so I won't get into the details of this. In the missing data tab, you have several options. Either you ask the software not to accept missing data if it comes across missing data and data you selected in the field, or you can ask it also to remove the corresponding observations before running the test. And you have other outputs and charts. So I will click OK. And I get this very famous p-value here, which I can interpret by stating this. The p-value is lower than alpha. We can reject the null hypothesis and accept the alternative hypothesis. Here's the answer to the question. The two treatments, drug and placebo, result in significantly different means of systolic blood pressure. And the risk of being wrong when stating this is very low, is proportional to the p-value. So there is a significant effect. So that was our first case investigated. You should know that the student's t-test dialog box allows for different charts you can draw. For instance, the means chart. You have the mean for drug and mean for placebo and error bars appearing at the top. And you can also place the p-value above. Let us move on to another case. Now we're going to investigate the effect of a qualitative variable on a qualitative outcome. So we're still in the same data. 3 weeks after having administered the treatments, we check whether patients recover or not from their disease. Question, is there an influence of treatment on recovery? So we still have one patient per row. It's still the same data set, but I just added this column. We have two independent variables now, systolic blood pressure, which is quantitative, and dependent variable recovery, which is qualitative. Now the goal is to investigate the effect of treatment on recovery. Let me go back to this table here. We have a qualitative independent variable and a qualitative dependent variable. So we're in this situation. We can use the tests on contingency tables, such as the chi-square or Fisher's exact test. So let us describe the data first. How to describe the link between two qualitative variables. So if you go back to this descriptive statistics guide I've showed you at the beginning of this PDF, you will come across a contingency table, which basically looks like this. In a contingency table, focus just on this one first, you have the two qualitative variables which are split in rows and in columns. So in rows, you have the treatment variable here, so drug and placebo, and in columns, the outcome variable, so recovery, no, and yes. Each cell includes the number of patients which are concerned. We have 24 patients from the drug group who recovered, for instance. We have 13 from the placebo group who recovered. We can also express things in terms of percentages, which can be a bit more interesting and a bit more readable. So, for instance, 60% of patients from the drug group recovered. And on the other hand, in the placebo group, only 32% of patients recovered. Now, the statistical test involved also has null and alternative hypothesis. The null hypothesis, percent recovered in drug group equals the percent recovered in placebo group. So we have similar proportions here. So this is one way of expressing the null hypothesis. It's not necessarily the most correct way, but it's the most intuitive one, at least. In the alternative hypothesis, you have an idea of a difference. So it's exactly the same, but with a difference here. So you can also show things in this chart. On the y-axis, you have percent recovery within each group, drug or placebo, and the colors correspond to no and yes, recovery no and recovery yes. You see that for patients who took the drug, you have a bigger proportion of people who recovered as compared to the placebo. Now, let me show you how to run descriptive statistics and statistical test at the same time on this data. I will go to test hypothesis and correlation association tests. Tests on contingency tables. Here we are. So first, we need to select the data format we have as an input. Do we have qualitative variables, or do we have a contingency table which is already ready? No, we have qualitative variables. So we need to select one variable which will be in the rows in the contingency tables, and the one which will be stored in columns. So traditionally, we put the independent variables in the row variables of the contingency table, and the outcome, which is recovery, as a column variable. In the options, I will be able to choose the test that will answer my question. So the investigation of the link between the two qualitative variables. There are many, chi-square, likelihood ratio, Monte Carlo method. I would recommend using the Fisher's exact test, which is quite robust, which has much fewer conditions of validity than the classic chi-square test. So I would recommend using this test. In the outputs tab, you can ask for the contingency table, for instance, for association coefficients. You can ask for the proportions or percentages per row and per column. Be a bit interesting. And in the charts tab, you can also ask for different kinds of charts, such as the one I showed you on my presentation. So I click OK, and I get my contingency table right here. I get the percentages per row. Okay, this is what we've seen in the presentation with the chart. I can also compute things in columns. So among the people who did not recover, what is the percentage of people who had the drug and the percentage of people who had the placebo? And the same thing here. So you have this inverted chart right here. And at last, Fisher's exact test, which is linked to a p-value, which I will interpret here. So the null hypothesis percentages are equal. Alternative hypothesis, the percentages are different. The p-value is lower than alpha. We can reject the null hypothesis and accept HA. So we can say that percent recovery of patients using the drug is significantly different from percent recovery of patients using the placebo. In other words, recovery depends significantly on the treatment. We saw how to investigate the effect of one qualitative variable on one quantitative variable, the effect of one qualitative on one qualitative. Now we will see one last case for today, how to investigate the effect of one quantitative variable on one quantitative outcome. So we'll be using a cohort analysis data set, which is also made up, which is called surgery success rate of smokers and non-smokers. 15 smokers undergoing a specific surgery in the near future are compared to 15 non-smokers undergoing the same surgery. So we set a group of smokers and a group of non-smokers who will undergo a surgery in the near future. And we followed several physiological variables, A and B, for instance. And at the end, after the surgery, we measured some score that measures the amount of success of the surgery, a score from 0 to 100 for each patient. So once again, we have a dependent variable or a clinical outcome, which is surgery success score, and you have independent variables. Okay, smoker, physiological variables. The question we ask, does physiological variable B influence surgery success score? So this is a quantitative versus quantitative question. What is suggested in the mainstream statistical methods in this guide is using linear or non-linear regression. You should know that there are many methods available out there, and I'm just showing you the most mainstream ones, and sometimes linear regression is not necessarily the most appropriate method according to the data you have. So let us first describe the data. Now we are on cohort analysis here, this tab. I'm going to describing data, descriptive statistics once again. So I want to describe all of the quantitative variables according to smoking status. So 0 or 1. Then the outputs, I'm going to keep all of these. As soon as you select several variables in the general tab, I would strongly suggest unchecking this option here, display vertically. You will have a prettier output. Then the charts, once again, I'm going to ask for scattergrams, strip plots, box plots, and I will group plots. So let me click on OK. So we get our different statistics. For each variable, here we have the physiological variable A. We have the statistics for the 0 group and 1 group. 0 is non-smokers and 1 is smokers. Same thing for variable B and for surgery success score. So obviously, if we check already the minimum and the maximum, we may say that nothing is alarming. And then if we compare the mean success score for smokers versus non-smokers, we see that the success score seems higher on average in non-smokers as compared to in smokers. Then you have the box plots, you get the box plot, the strip plots, and the scattergrams. I won't spend time commenting on these, but it's always very interesting to look at them. I'm going to show you another way to describe things. In this case, I'm going to describe the link now, the pairwise links between all of these quantitative variables while accounting for the qualitative variable. I'm going to correlation association tests and correlation tests. Here in this field, I'm going to select all of my quantitative variables, which I will describe according to the smoking variable in the subsamples field. In the charts tab, I'm going to ask for scatter plots and matrix of plots. And I click OK, and you will see what I get. You get a chart that looks like this. In rows, you have the quantitative variables. You also have the same quantitative variables in columns. Each scatter plot corresponds to a scatter plot linking the two corresponding variables. So here on the y-axis, we have physiological variable A. On the x-axis, we have physiological variable B. Here we have the surgery success score on y, and on x, we have the physiological variable B. Okay, and then the color corresponds to the smoking status. This is the chart corresponding to the question I asked in the beginning of this last part of the webinar. So I wanted to investigate the effect of physiological variable B on surgery success score. Usually the dependent variable or the outcome is placed on Y and the independent variable is placed on X. So we may expect that there is an influence of physiological variable B on surgery success score. So the higher the physiological variable B, the lower the surgery success score. How to assess the effect of the independent variable on the outcome? I'll be running a linear regression to answer this question. So a linear regression model can be written like this: y equals a plus bx, and can be represented by this line. So on y you have the outcome, surgery success score, and on x you have the explanatory variable or independent variable, which is physiological variable B. So A and B are parameters or coefficients which will link this variable to this one. Now let me rewrite this down by using real variable names. Success scores equals A plus B multiplied by physiological variable B. Okay. So this is the dependent variable, which is also called the y variable. This is the independent variable, also called explanatory or x variable. A and B are the regression model parameters or coefficients. how can we interpret A and B? A will be the intercept. It will be the y coordinate of the intersection between the model line and the y-axis. B will be the slope of this line. If B is negative, the slope is decreasing, or the line is decreasing. If B is positive, the line is increasing. If B is close to 0, then the line is flat. Usually in statistical modeling, you are able to capture one part of the reality, but there still is one part of the reality you are unable to capture using your model. And this part of reality is called the errors or the residuals. It's all the differences between the points and the model or the line. So this is the part of reality that you are unable to capture using your model. Now, we used linear regression. This was not necessarily mandatory. The question allows to choose a model which is maybe less linear if the data and the interpretation provide enough justification for this. Imagine we had a relationship which is a bit more curvy. Maybe a model which is more curved would have been more appropriate than classic linear regression. So now let me run the regression in front of you. So I'll go to modeling data, linear regression. So most of the XRStat modeling tools are organized this way. You can select dependent variables in one field and independent variables in other fields. My dependent variable here is the surgery success score. My explanatory or independent variable is physiological variable B. There are many options in the linear regression dialog box, but I won't get into the details today. So I click OK. And also there are many outcomes that come out of this analysis. I'm going to focus on the most interesting outcomes, which are model parameters and a few charts which appear later on in the results report. Okay. Let us first focus on the model parameters. In this table, each row corresponds to one coefficient or one parameter. So here we have in y equals a plus bx, this is a and this is b. These are estimations of the parameters. So the software estimated the parameters. You see that b is negative. So we were expecting this. The slope is negative as we saw it on the scatter plot. The line was decreasing. Now, pay attention to this column here. These are p-values. These are p-values that assess the significance of each parameter. And the null and alternative hypotheses are as follows. So for each parameter, the null hypothesis is parameter equals 0, and the alternative hypothesis is parameter is different from 0. So if I focus on the p-value linked to the slope here, I can say that this slope is significantly different from 0 as the p-value is very low. So the line is significantly decreasing. Then you have confidence intervals around the estimates because, of course, you are estimating a relationship from a sample and not from the whole population of patients. This is the equation of the model. So y equals a plus bx. So y equals a plus bx. You can use this equation to predict success score according to new values of physiological variable B. So if you have one new patient who enters the surgery room that has a specific value of physiological variable B, you will be able to compute the surgery success score out of this equation. But of course, you need to have good predictive quality of the model to be able to do this. So some more elements of interpretation. Success score significantly decreases with physiological variable B. The associated coefficient is negative and significantly different from 0. Now, how to interpret this specific number now? In other words, when physiological variable B increases by 1 unit, the success score will decrease by 1.808. The intercept is positive and significantly different from 0. This value corresponds to the y-coordinate of the intersection between the regression line and the y-axis. And more concretely, it's the value the success score takes when physiological variable B equals 0. So sometimes it's a bit surrealistic, but sometimes it can make sense. You get also this result at the bottom of the report. This is the regression line in the middle, which is bounded between two confidence intervals, confidence envelopes, a narrow one with dashed lines and a thick one with complete lines. This is the confidence interval. Sorry, let's start with the narrow one. This is the confidence interval of the model linked to parameter estimation. So in the population of patients, the model has 95% chance of being between these two lines in this envelope. This is the confidence interval of the prediction. If you want to use this model for the prediction, this is the uncertainty you will have in your predictions. So this is maybe not a very appropriate model to predict new outcomes of surgery success scores, as the confidence envelopes for prediction is very, very thick. You have one value appearing here. This is the R-square. It reflects goodness of fit, and it's bounded between 0 and 1. So the closer the R-square is to 1, the narrower the points are dispersed around the line. And then the closer R-square is to 0, then the more dispersed are the points around the line. Of course, you have some assumptions you need to check so that your model is reliable. You need to check the linearity of the relationship between y and x if you are using a linear model such as regression, scatter plot, but you should also check more assumptions about residuals, independence, normality, not too many outliers, and homoscedasticity. I won't get into the details of each of these assumptions. So for more details, I would suggest checking the webinar on statistical modeling. So go check the recording. But you should know that this chart, which is produced in the regression report and which represents standardized residuals according to the predictions, allows you to check for the quality of the residuals. The dots or the points need to be homogeneously spread around the horizontal line here. So you shouldn't be seeing specific patterns on this chart so that the model is valid. In our case, there may be one point which is a bit too far away from the bulk of the points. So this is maybe a specific outlier we should be checking out and maybe removing from the analysis if this patient is not necessarily representative of our population. So to sum up, study designs are a set of methods and procedures used to collect and analyze data in the framework of a particular research problem. And there are many study designs, which include all of these. Analytic study designs involve independent variables and outcome-dependent variables. These are designs we've seen today. This is an analysis process, suggestion, describe and clean the data, very important, then assess the effect of the independent variable on the outcome. And you can use the two guides I gave you in this presentation to choose one mainstream method. Otherwise, you can look for other methods which may be a little bit more appropriate for your specific data and questions. And we've seen many tests and models that are linked to specific situations. What are we going to see tomorrow? 3 exciting things we'll be seeing next. First, going multivariate. Why? We're going to investigate the effects of several independent variables on one specific variable. Why is it interesting to do so? Then we'll see a case of how to model binary outcomes using several independent variables. How to model, for instance, the disease, yes or no, the recovery, yes or no. Then, at last, we'll be investigating survival analysis or how to model time to event data. I thank you all for attending, and I really hope I'll be able to talk to you again tomorrow. I hope you enjoyed, and I wish you a very good day.